Hi, I'll be talking about list decoding of LDPC codes. This is joint work with Nicolas, Noga Ron-Zewi, Shashwat, Silas, and Mary Wootters. I'm Jonathan Mosheiff, and let's begin. Our first order of business is to define what is list decoding. And for this, we need to first quickly recall what is an error-correcting code. So a Q-array error-correcting code is a subset of the n-dimensional linear space over the finite field FQ. In a classic use, Alice and Bob want to communicate from afar, presumably because they need to keep social distance during a worldwide pandemic. So here the code words are in blue. Alice sends Bob a message X from the code. And due to some noise, Bob, instead of receiving X itself, it receives some noisy version of X. Now, assuming that the amount of noise is not too large, Bob can search for a code word near the word that he received, and then he manages to correct the message back to X. This is known as decoding. The rate of the code is log of its size over n. And we want the rate of the code to be large because that allows for more efficient communication. But on the other hand, the larger rate means that there are more blue dots, so it is harder for Bob to correctly decode the received word. So in other words, codes of larger rate can also handle less noise, and that leads to an important trade-off. Now, throughout this talk, we are always going to think of codes where n is going to infinity and the size of the alphabet q is going to remain constant. Having said that, we can now go on to define what is a list-decodable code. So the noise model we'll work with today is an adversarial noise model with some fixed noise ratio p. So in other words, we assume that after Alice fixes the code word X that she wishes to send Bob, some evil adversary is allowed to choose a p portion of the symbols in X and just change them as they please. And in order for Bob to always be able to recover X that Alice is sending in such a noise model, the code needs to satisfy the condition that every radius p Hamming ball in FQ to the n must contain at most one code word. And this condition allows what's known as unique decoding, because Bob can uniquely determine what's the word that Alice wanted to send. Now, motivated by unique decoding, list decoding is a natural relaxation in which we just allow each Hamming ball of radius p to contain at most L code words for some small constant L, rather than only one. And we're going to require that L has little or no dependency on n. And this means that while Bob cannot uniquely recover X, he can produce a small list of possible messages, and he knows that the message Alice wanted to send is in this list. Now, list decoding is natural and very strongly motivated notion, and it has many classical applications in computer science. So having defined what is list decoding, an obvious question is whether there exist list decodable codes and to what degree are such codes list decodable. So giving a noise ratio p, the threshold 1 minus the Curie entropy of p is known as the capacity of the channel. The list decoding capacity theorem tells us that there exist codes of rate epsilon below capacity, which are list decodable for noise ratio p with list size roughly order of 1 over epsilon. And this theorem is tight in the sense that no code of rate above capacity is list decodable for noise p with any reasonable list size. The list size in that case would have to be exponential in n, which is completely impractical for anything. Okay, so this pretty much, not exactly, but pretty much settles the question of whether there exist combinatorially list decodable codes. But a more complicated question is what happens algorithmically. So consider the job that Bob has. He's given some word y, which is a noisy version of the word that Alice wanted to send him. And he needs to find all the words in the code that are of Hamming distance at most p from y. And this is how he compiles the list, the list decoding list. So the combinatorial theorem says that there are codes where only a small number of words are p close to y, but it doesn't tell us what Bob needs to do in order to find these words. And what we're looking for is a code which satisfies the combinatorial theorem, but is also equipped with an efficient algorithm that, given y, actually finds a list of code words that are p close to y. Now, the combinatorial theorem is classically proven by taking a random code, which is just a random subset of fq to the n of the appropriate size. And the problem is that a list decoding algorithm for such a code would have to take time exponential n, which is very large. Now, a random linear code is a random subspace of fq to the n, and it's more structured than just a plain random code because it's linear. And more precisely, we define a random linear code of rate r as just being a subspace uniformly sampled from among all the Rn dimensional subspaces of fq to the n. Now, a more sophisticated line of work shows that random linear codes are combinatorially list decodable with roughly the same parameters as those of plain random codes. However, even for such codes, it is highly unlikely that a polynomial time list decoding algorithm exists. Guruswamy and Rudra actually came up with folded Reed-Solomon codes, which are list decodable, algorithmically as well, in polynomial time in n, but still not in linear time. And finding a linear time list decodable code, which is also capacity achieving in the sense that it satisfies the combinatorial theorem above, that remains a major open question. And our motivation in this work is to somehow advance this question. And this leads us to our next subject, which is a more specific, more structured family of codes known as Gallager's ensemble of LDPC codes. So in order to explain what are LDPC codes, I first need to give you another way of describing any linear code. And that's the graph view of a code. So a code is linear if it's just a linear subspace of fq to the n, and a linear code is defined by linear constraints. So one way to describe the linear constraints that define a given linear code is using a bipartite graph. So on one side, on the left side, we write the n message nodes, the n message symbols, sorry. So these are just elements of fq. And we have edges between a node on the left and between certain nodes on the left and certain nodes on the right. And these edges are labeled by elements of fq. Now, to each node on the right-hand side, these are called constraint nodes. So to each constraint node, we assign a value that is just the linear combination with the corresponding coefficients to the edges of the nodes, of the message nodes that are connected to the given constraint node. So for example, here, constraint node number 1 is going to be a linear combination of message nodes 2, 4, and 5. Now, we say that a word belongs to the code if by writing it on the message nodes and then evaluating the values of the constraint nodes, every constraint node gets the value 0. And what I told you until now is really just like a graphical way to write the parity check matrix of any linear code, so it didn't really add much. However, more interestingly, if this graph is sparse, in the sense that every constraint node has degree at most s for some small constant s, then we say that the code is an SLDPC code, where LDPC stands for low density parity check. And importantly, LDPC codes are the only class of codes for which we have any linear time unique decoding algorithms. Now recall that unique decoding algorithmically can just be thought of as a special case of list decoding where the list size is 1. So it's computationally, it's an easier problem. So that means that while we don't know of any algorithms that do general list decoding in linear time, LDPC codes sound like they would be good candidates. However, the caveat is that combinatorially, we didn't know until the current work, we didn't know of any LDPC code which even achieves combinatorially good list decoding, like actually anything anything more than just trivial bounds for list decoding. And in this work, we remedy that. We are going to find a family of LDPC codes which are list decodable with arguably optimal parameters. Okay, so this family that I'm going to describe to you now is a certain family of LDPC codes. It's called Gallager's codes, and it's actually the first known family of LDPC codes discovered by Gallager in 1962. To describe what's a Gallager code, we need two parameters. So one is S, the sparsity of the code, and that's just the degree of the constraint nodes, which we already talked about before. And there's also going to be another parameter T, which counts layers. And in 2 minutes, you're going to know what that means. So we first describe what we mean by a layer here. So a layer just consists of n over s constraint nodes, which we connect to the message nodes by choosing some random s to 1 matching and putting non-zero coefficients on the edges. Now, to construct the whole Gallager code, we sample T layers independently in uniform. So this is a random construction and yields a code which is certainly an SLDPC code, and we call the resulting code a random Gallager code of sparsity S. Now, note that such a code has exactly Tn over S constraint nodes because each layer consists of n over S constraint nodes. So the rate of the code is going to be 1 minus T over S. And in particular, we're going to want T to be less than S. OK, so having defined both list decoding and Gallager's code, we can now state our main result about list decodability of Gallager codes. OK, so originally, in Gallager's seminal 1962 paper, he proved that combinatorially, his LDPC codes achieve unique decoding, which you can recall is just list decoding with list size 1, with rate up to 1 minus the entropy of 2p. And this is known as achieving the GV bounds. And that's a classic bound. It means basically that Gallager codes have similar unique decoding trade-off to that of random linear codes, which is excellent. However, because Gallager codes are less random and more structured than random and linear codes, this combinatorial result is also accompanied by a linear time algorithm to do this unique decoding, which doesn't exist probably for just random linear codes. So our main theorem can be seen as an extension of Gallager's result. We're stating that Gallager codes are with high probability also combinatorially list decodable with very good parameters, which are similar to the list decoding parameters of random linear codes. So we're just taking Gallager's statement and extending it to list decoding rather than just unique decoding. And our hope is that like what happened in the case of unique decoding, we can also manage to eventually come up with an efficient list decoding algorithm to accompany this combinatorial result. So that was an informal statement of our result. Now we're going to want to prove it to state it more formally. And I'll start giving the more formal statement. And while I'm at it, I'm also going to talk a bit about our proof techniques. So essentially, our main theorem is a reduction from a question about Gallager codes to a question about random linear codes. So as we stated before, it is already known that random linear codes achieve list decoding capacity with list size order of 1 over epsilon. And our main theorem states that for every rate and list size and any delta as small as you want, there exists some sparsity parameter S null, such that whenever a random linear code of rate R is likely to be PL list decodable, then a random Gallager code of rate just R minus delta, just slightly below R, is also likely to be PL list decodable. And I can tell you that we can even, in fact, take this S0, this S null to be not very large as a function of R delta and L. So this theorem is just a reduction. It says, okay, if you found parameters for which random linear codes do a good job of list decoding, then you can take a Gallager code with very similar parameters, and it's also going to do a good job of list decoding with the same parameters. And since we already know that random linear codes do a good job of list decoding, then this proves that Gallager codes do a good job of list decoding. Okay, so I'm going to talk a bit about our proof method and some results related to it, which are actually of independent interest. So our proof method goes through a notion called a local property of a code. That's a new notion. And to motivate it, let's try to characterize list decodability of a code in terms of the code avoiding certain bad tuples of code words. So what I mean by a bad tuple is the following. A bad tuple consists of L+1 vectors that are all at most p close to some joint center y. And recall that just by the definition of list decoding, a code C is list decodable if and only if no such bad tuple exists in the code. Now, an important property of these bad tuples is that they're close to coordinate permutations. So by coordinate permutations, I just mean taking, these are vectors in FQ to the n, so each is of dimension n, and just imagine rearranging their entries, but applying the same rearrangement to x1 all the way through to xl+1. So we have l+1 vectors, and we apply the same rearranging function to each of these. And it's not hard to see that if you take a bad tuple, x1 to xl+1, and apply the same rearrangement to all vectors in this tuple, then you get another tuple, which is also bad. So we call such a set of tuples invariant to coordinate permutations. So now we're going to make the following generalization. So let B be some set of bad k-tuples that is invariant to coordinate permutations. And we're going to define a property PB. We're going to say that a code satisfies PB if the code avoids containing any bad tuple. So it doesn't contain any tuple from B. Such a property PB is called a k-local property. And we've just shown that being PL list decodable for any PLL, for any 2P and L, is just an L+1 local property. And another natural close relative of list decoding called list recovery can also be seen very similarly to be a local property. Now, in fact, the reduction that I stated before from LDPC codes to random linear codes is more general. It applies not just to list decoding, but it actually applies to any local property. Now, as part of our proof, I want to tell you about one of our main lemmas, which is actually can be considered a theorem. I'll call it a sub-theorem. It's pretty much a theorem by itself, and it is of independent interest. So this is a theorem about local properties in random linear codes. And it has nothing to do directly with LDPC code. However, it does help us improving the main theorem about reduction from LDPC to random linear codes. So this sub-theorem says that local properties have sharp thresholds for random linear codes. What do I mean by that? So let P be some local property. And if you look at the lower left, let's draw a graph of the probability that a random linear code of rate R satisfies the property P. So here R is the x-axis, and the probability is going to be on the y-axis. Then what our theorem says is that there's going to be some threshold, which we're going to call RP, that's a threshold rate, such that if the rate is up to RP, then the probability that the random linear code satisfies P is going to be very, very close to 1. And then around RP, it very rapidly declines and becomes very close to 0. So this is called the threshold phenomena. And actually, such phenomena are very ubiquitous in other random models, and most famously in random graph models where these are very widely studied. Importantly, besides just showing that a threshold exists, in this theorem, we actually characterize the threshold rate RP in terms of certain expectations. It's a very natural characterization, and it's going to serve, this characterization actually serves a crucial component, as a crucial component later in our proof of the main theorem about the reduction from Gallager to random linear codes. And finally, I just want to note that this sub-theorem has actually already been applied in some other works since we originally submitted this paper. So it was applied in some works that are also related to list decoding and list recovery. This concludes the discussion of our results and methods. I would like to finish by presenting a few open questions that arise from this work. So first, we've mentioned list decodability and list recovery as two important properties of codes. But it would be interesting to understand what other natural properties are local properties, since our results and maybe also future research using similar methods can be generalized to any other local properties as well. Another question also relating to local properties is that, so the notion of local code property is probably new to this paper as far as we know, but it has some well-studied analogs in other fields, as I mentioned, particularly graph theory. And specifically, our result about thresholds of random linear codes is really analogous to a specific classic theorem about random graphs. And we would like to put all of these results together within a more general framework. And in particular, I hope that since the graph analogy is so rich and so studied, maybe just by understanding it better, just by understanding the analogy better, we can also reach more interesting discoveries about codes. Another question is whether our proof can be de-randomized. So we'd like to understand whether any deterministic construction can take the role of a Gallager code in our proof. And that would effectively de-randomize the construction. And in particular, this may be helpful in solving our original motivating problem, which is finding a linear time list decodable capacity achieving code. Okay, so thank you for listening to this talk, and see you all at Fox. Bye.